All right, PPP. PPP is point-to-point protocol. It is actually one of the first access protocol much before Ethernet. Before Ethernet, all we had was point-to-point links, and the protocol that was run on the top of that was called PPP. However, even though Ethernet is here, but we still use PPP because there are lots of point-to-point links. And even when you have point-to-point links, you still have the you still need the framing and other things, so that so you need a data link protocol. So it was used for user to network connection, and so mostly this was designed so that you could dial into an ISP, and from there you will get onto the network. So this was designed for dial in. And it is used for router to router connection. Even though the routers to router connection, they don't dial in, there is a physical link always present, but they use PPP. So PPP has three components: data encapsulation, link control, and network control. All right, these are described later on: NCP, LCP, and the encapsulation. But before we go to the protocols, the link itself is normally dead, means not connected. But whenever you dial in, the first thing you do is you try to establish a connection. So you go to the established state. This is the state diagram. And if you fail, you go back and then try again, and 1 minute later or whatever. But if you succeed, then first thing you have to do is authenticate. Give your password. If your password succeeds, then it is disconnected, and then you can try again later. Or if the password fails, right? If password succeeds, then you go to the network layer, and then there you probably do something like DHCP or find an IP address or something like that, and then you remain there forever as long as you are connected. You keep using that IP, and then once you are done, you close the connection and you go back to this. So the first question is, everybody understands this state diagram, that the link could be dead, link could be establishing, could be authenticating, could be in the network state, and could be in terminate state. Most of the time it will be in one of these two states.
What's the difference between a terminate and dead?
Yeah, termination is a closing. It's basically, bringing it down. So, that is all the time. Termination is closing of connection. It's like a close message, yeah. Go ahead. Your question, yeah.
It's weird because there's the arrow that does closing, and then another arrow which does down. Why there's just one closing arrow that goes to dead?
No. The thing is, so these will terminate the connection in the sense that you say termination is the link is up, and so this is basically dial down the telephone or whatever you want to go, put the telephone down, something like that. Whereas this is telephone is already down. Yeah.
A missing arrow in the network going to itself as long as it's active?
Yeah, right. If you want to put that, you can just keep going it forever. That's this state, but there is no event that keeps it. The thing is, there are only two events: one closing when you get out, and one success when you get in. Everything else, you remain in this state by default anyway.
Yeah, but most of the other states looks like transition.
But there is no. We haven't shown any state. The thing is, everywhere you come in and get out, and we haven't shown how long you stay here. So this one actually, I think, is correct. But your interpretation is correct. You could put that everything else you just keep going there, but there is no event there. Basically everything else, whatever happens, you stay there. All right, so let's see. I think we already talked about this one. The PC modem calls the internet, the provider sets up the link, and then you send the LCP packets. You set the LCP packets. Once you're done with LCP packets, then you authenticate, and then you send the NCP packets. Once you get the NCP packets, then you can send the IP packets. So there are three kinds of packets you can send: LCP, NCP, and IP. Let's see, we have them. So first thing PPP does is that it provides the framing. So what is a frame? So on the wire, bits are always going. Even if you are not sending anything in many networks, when the bits are going, zeros are going all the time, or something like that. So suddenly some zeros become 1. How do you know that this is the beginning of a new frame? So you need to put some bit pattern which will not appear inside the frame. Just like this, if I paint a picture here on this wall, how do you know where the picture begins and where the picture ends? I have to put a boundary around it, a colored boundary, so that people will know that this color is not part of the wall and this color is not part of the picture. Right? At homes you find a wooden frame to put around the picture so that you can distinguish the picture from the wall, right? So similarly in the computer framing we put a frame character, and we ensure that that character never happens inside the frame or outside the frame. It only appears at the boundary. That is called framing. So what is that character? All right, so that is what we need to do, and we'll come back to that. What is that character? So framing is how do we convert bit streams to frames. So now once we have that character, then we know that this is the beginning of the frame, this is end of the frame, and we can calculate the CRC and we can check the source address, destination address, everything, right? So we need the framing. Protocol multiplexing. Another thing PPP allows you is that many users can use the same data link. So you could be running IP, somebody could be running Mac, Apple Talk, somebody could be running Xerox, XNS. There are other layer 3 protocols that could be running on the same PPP. And so that is done by PPP. Bit transparency. PPP should allow to send you any bit. So what about how do you send that character which is framing character inside a frame? So that's the problem they have to solve. Error detection. So they decided that we want to make sure that every frame is delivered correctly. If it is an error, PPP will say that it is an error. So it has to have a checksum. RCRC, something like that. But they decided they are not going to do a correction. So no corrections is required. These are the requirements. Liveness. So whenever the link fails, it will tell the users that the link has failed. Otherwise the link is up. And then the link layer address negotiation, network layer address negotiation. When you come on first, you don't have an IP address, so it somehow gives you facility so that you can get the IP address. All right, and non-goals. And this was the non-goals where that they will not try to correct the errors, they will not try to recover the errors, so they are not going to do any retransmissions. That was their decision. No error recovery. No flow control. That was their decision that we are not going to use any Windows stuff, etc. No out of order delivery. Okay, so if you lose some packets, you get 1, 3, 5, 7, 9. That's okay. No need to support multi-point links. So PPP was not designed to support multi-point links like Ethernet, where multiple people will be on the same line. All right. So this was the PPP design goal, and this is how it is done. There is a bit pattern, 1 0 followed by 6 ones followed by a 0. This is the framing character. All right, a 0 followed by 6 ones followed by a 0. Whenever that character happens, that means it's the beginning of a frame or end of a frame. Actually, the same character is used for both beginning and the end and the middle. In the sense that if you have 2 frames, you will have that character. By the way, let's call it flag. That is what it is called, or you can call it 7E. Either way, so 7E is the character. So flag, you will have a flag, frame, a flag, next frame, flag, next frame. So you don't need 2 flags. You could have 2 flags, but I mean, you just 1 flag will do. So a flag is the delimiter end of the frame if it was going, or the beginning of the frame if it was not going. All right, so there is a flag. Now, so the next question is, what do you do if there is a flag inside the data? Right? So there is a rule called Byte stuffing rule. If you find 7E inside the data, replace it with 7D5E. So 1 character is replaced with 2 characters. Frame becomes longer. Now what happens if you find 7D in the data? If you find 7D in the data, then you replace it with 7D5D. All right? These 2 rules are sufficient to take care of all possibilities. All right? Now you can use any characters inside the frame. The sender replaces all 7 E's by these two and all 7 D's by these two. And the receiver does exactly the opposite. Whenever it sees 7D followed by 5D, it knows that it is one 7D, and whenever it sees 7D followed by 5E, it knows that that's a 7E. So these are all data frames. However, if it sees 7E by itself, then it knows it's flagged, and if it sees 7D by itself, then it's known as an error, because 7D should not appear anything other than 7D followed by 5E or 5D. Only two possibilities. All right, so just verify yourself to your satisfaction that these two rules are sufficient to send any data pattern. This is called byte stuffing, and the byte stuffing as described in the book is incorrect. Yeah, basically, it's very simple. Okay, everybody who is talking, please talk to us so that we can understand. Hold on, I have to answer the question, I will come to your question. The question was, can I explain it again? So I'm going to explain it one more time. The flag is 7E. If 7E ever appears anywhere here, from between the flags, so these two flags are okay, but anywhere in the address, control, protocol, information, padding or CRC, we replace it with two characters, 7D followed by 5E. Also, second rule is if I see 7D anywhere in these two, I replace it with 7D followed by 5D. Okay. Now, when it comes back to the receiver basically looks for, if anywhere it finds 7D, it looks for 5E or 5D. Right? And if it finds 5E, it knows that it's the 7E part of the data. Right? It is in the middle of the frame, it will send 7E to the application, whatever is using this link. And if it finds 7D, 5D, it sends 7D. If it finds any other combination following 7D, it will think that the frame is broken and throw away the frame. That's invalid coding. Okay? All right. So that's all. Okay, next question. You understood? Okay. All right. Any other question? Yeah. Go ahead.
So how long is 75E? How long is that in bits?
70. Okay. So here I think each of these is hex character. Each of these hex character means 4 bits. 7 is 4 bits. E is 4 bits. Each is 8 bit. So basically these things are 8 bits. One 8 bit is replaced by 16 bit. 8 bit is replaced by 16 bit. 1 byte is replaced by 2 bytes. Huh?
Does it read it one byte at a time? Then when it sees 7D?
Yeah, see, the thing is, it will not read 1 byte at a time. See, the thing is, PPP is a data link. Okay, so, okay, hold on. First of all, it is reading all these bits. And suddenly it finds 0 followed by 7 ones or 6 ones followed by 0. That is the beginning of a byte. Then it is on the byte boundary. All right? And then it is reading in the bytes.
So then it reads how many bytes at a time?
It will read 1 byte at a time or maybe 2 bytes at a time.
But if it read 1 byte at a time, then not work?
Yeah, not 1 hour. The thing is, if it finds 7D, then it will read the next byte.
Oh, okay.
You cannot interpret 170 with anything. Yeah.
So 7D is never followed by any other character?
No. Because if, I mean, just think about it. If there was a 7D followed by 4E, what will happen? Anybody?
7D, 5D, 4D.
Yeah. Yeah.
Is the flag always 7E or is that just an example?
Now the question is, the flag is always 7E or it could be different?
Yeah.
No, it is always 7E.
Why are we using hex?
By using hex, because 4 bits are easier to explain in hex than decimal. Okay? All right. So now so first we understand the framing. The next field is address. Now the address is meaningless. When you have a point-to-point link, I'm talking to you. I mean, all the packets are going to you, right? Every packet coming from you is coming to me. So why we have the address? Well, at some point they wanted to make it multi-link, means multiple people on the same link. So they put the word address there. So your address is 1, your address is 2, your address is 3. They thought that way. But since there are nobody else, we mail every packet is broadcast packet. Okay? Every packet is a broadcast packet. Control. Control has something to do with what is this packet about. It could be some message between the two devices, and generally it is always 3. Protocol is what is the protocol that is running on PPP, and there is a number for IP. I forget the number, but it could be 80 from my memory, but I could be wrong on that one. And then the information, which is basically whole IP packet, followed by padding to make it so that it is 1 byte boundaries. Then there is a CRC, and CRC is 16-bit, not 32-bit. Yeah.
Could you explain again that control?
Yeah, control basically is the type of the message.
What do you mean type of message?
Well, different values will indicate different things to do with this message. But right now it is all 3. 3 means unnumbered. I don't want to go into detail, but there are 3, 4, 5, and nobody uses 4, 5 at all. I mean, I have never seen anything used other than 3. 3 is unnumbered message. Unnumbered means there is no sequence number. That's all it means. So I mean, this is just a datagram. And so this is always broadcast. This is always 3, and then protocol. Protocol is the higher layer protocol, and then information, which is basically the whole packet, higher layer packet, followed by padding, followed by CRC, which is 16-bit, but 32-bit can be negotiated using LCT.
When you're saying higher level packets, like the IP packet?
Yeah, IP, you could be running something else. You could be running, for example, Apple Talk, which is competition to IP.
Yeah. So if I have a dial-up connection at home, I'm using, what's the name of this?
PPP.
No, but that's just a generic PPP message?
So when you are dialing up, you are connecting PPP, and if you are using Mac and you are connected to a Mac server, you will probably be using, I mean, nowadays Apple also uses IP, by the way, but there was a time when Apple used Apple Talk, and Xerox used XNS, Digital uses something else, so everybody could go on the same PPP.
So it re-encodes the data inside the IP packet so that the 70 flag would be inside it?
No, IP packet is here. This is IP packet.
Right, but it gets rid of the 70 inside it?
Yeah, get rid of 70 inside it.
Okay.
All right, CRC and flag. So CRC is 16-bit and then the flag. So key thing to notice here is framing and multiplexing. So PPP provides you multiplexing of what? Multiplexing of different protocols. Right, so there is a protocol field, and it provides framing by putting the flags. That's all. Anything more about PPP anybody wants to know? I mean, maybe you can read the book a little bit, but that's the key thing to know, is the byte stuffing. Yeah.
So how does the error detection, is that just the CRC?
Yeah, it does have a CRC, not checksum. It has a 16-bit CRC, so there is a polynomial. There is a 17-bit number that is used to divide. And so it has error detection, no correction, no retransmissions, nothing like that. Okay, so here we go from the oldest protocol to the newest protocol, MPLS. MPLS is very new. I mean, like 10 years new. I mean, just 10 years old. And it stands for multi-protocol label switching. And let me just tell you how it came about. So about 16 years ago, telephone companies decided that it looks like IP packet switching is very good, and they were doing circuit switching. Is very good, but it's not good enough for telephone companies, so they designed an own protocol called ATM, which we skipped. And ATM was something halfway between circuit switching and packet switching. And then they said we can do a lot of stuff with this that IP cannot do. So IP guys got together and they took all the ideas from ATM and they designed MPLS. So they said we can do the same thing that you can do. And so MPLS is actually again a mixture of circuit switching and packet switching. So this is how it works. And let me go back to the phone company first. In the old phone company days, everybody had a PBX. What is a PBX? Anybody knows? Private Branch Exchange. That's the phone switch you will keep in your company. So you might have just 3 telephone lines or and you might have 3 telephone lines coming in from the phone company, but you will have 30 phones. So you need a switch so that 3 people can connect to the phone line and the 27 are off anyway. So this is a private branch exchange. This is a switch, telephone switch. Then the telephone company had its own switches all along the network, and then they will end up in some other PBX. Now the idea is that there are lines connecting these switches, physical wires. These are physical wires connecting. And when you made a phone call, let's say you picked up line number 1. It might be connected to line number 3 here because that was available, wire number 3. At this switch, it was switched to wire number 5 because that was available. At this line, it was switched to wire number 2 because that was available. Then it was answered by wire number 3. So that is how it worked in the old phone network. It was circuit switched. There was a circuit, there was a wire that was selected all along. When they designed the ATM, they said we will use only one wire, which is very high speed wire, so it can have lots of all of this traffic on one wire, but we will put the circuit number on the packet. So they sent a circuit. So this red circuit in the ATM arena would have a packet with a number 1 in it. When it goes to the switch has a table and it says anything with a number 1 coming in, I should change it to number 3. Alright, this will have a table which says anything coming on number 3 should go on number 5, anything coming out with number 5 should go out with number 2, and number 2 should go out to number 3. So they could do the same thing as in circuit switching, but now with packets. Now these packets don't have destination address, by the way. Notice that 135 is not destination address. That's a circuit number. Right? And each circuit number could be, let's say, from 1 to 10, but you could have millions of destinations. Right? Because you could go 10 possibilities here, 10 possibilities, and it is not just always a straight line. There's a whole set of things which go up and down and everywhere, right? So the circuit numbers are not destination addresses. And circuit numbers are not limiting the number of destinations. Just like in IP, we have 32-bit limiting. Number of people who can talk IP. Right? So that limit is not there in telephone world. And there are lots of other advantages of having these circuits, such as guarantees. If you want to guarantee something, you can guarantee that circuit number 3 is 10 megabit, circuit number something else, red circuit, let's call it red circuit. Red circuit is 10 megabit, the blue circuit is 5 megabit, and that could be guaranteed. It's not possible to do that without the circuits. So the IP people said, okay, we can do the same thing. The main difference was that the ATM was fixed size packets. So ATM guys said that we will use 53 byte packets, 53 byte packet. And IP guys said, no, we don't need 53 byte. We can use whatever packet you have, but we'll put the circuit number inside it, and we will call it a label. And so that's why it is called multi-protocol label switching. MPLS is nothing but taking an IP packet, adding one more field on it, which is the circuit number in front of it. By the way, this description is not this way in the book. And I have simplified it, given you all this history simply because I spent 10 years of my life on ATM. All right? Now ATM doesn't exist anymore. That's why I didn't teach you. But if you go to my website, you'll find hundreds of papers on ATM. And ATM has become MPLS basically. So MPLS, each packet has a virtual circuit number, which is, by the way, these are virtual circuits because this one is virtual circuit number, 3 is virtual circuit number, white is virtual circuit number because there is really no wire number 3. Right? It's not a real wire, it's a virtual wire. So this is a virtual circuit number. It's called a label in the IP terminology, and these circuits are called label switched paths, LSPs. These circuits are called LSPs, and before you can send anything on LSP, you have to set it up. Just like on the telephone, you have to dial before you can say hello. You have to wait until the other party answers. Similarly, on the MPLS networks, you set up a connection. In IP, you don't have to do that. But on MPLS networks, you set up a connection, which most likely goes to the phone network anyway. And when these connections are actually set up probably permanently, they're not just dial-up. I mean, they could dial up, but nobody that dials up. These are, very high-speed net connections, so they just set it up permanently. And those are called LSPs. So once you set up the LSP, then you can do traffic engineering. What is traffic engineering? Traffic engineering means that I can decide which traffic goes through what path. With IP, you cannot decide that. With IP, all traffic takes shortest path. That means other paths are not used. The shortest path is congested by design. Right? With MPLS, now you can set up a blue circuit and you can set up a red circuit between the same source and destination. Right? And when the packets come in, they decide basically whether it is a blue packet or a red packet. Red packets will go that way, blue packet will go that way. So the packets will have the circuit number or whatever it is, and they will find the right circuit to follow. Yeah.
Is MPLS instead of IP?
Okay, so MPLS is what we call layer 2.5. It is in between Ethernet and IP. Ethernet and PPP are layer 2, IP is layer 3, MPLS is layer 2.5. So the MPLS header comes in front of IP.
So there will be like an Ethernet header, then MPLS header, and then IP?
Yeah, exactly. Why is called a virtual circuit? Because in this diagram here, this is a real circuit. There are really 8 wires there between the switches. Here, there is not 8 wires, there is only 1 wire. And we are saying that this red circuit goes on the circuit number 3. Really, it is not going on circuit number 3, it is going on circuit, whatever circuit number that is, right? So that 3 is a virtual number. Hold on. Oh, here we are dividing the wire. This thick wire is being divided into many thin wires.
Okay. In terms of bandwidth.
In terms of bandwidth, yeah. Yeah, go ahead.
The systems in the middle that do the forwarding, there are switches? Like the one
Okay, so they are MPLS switches now. They are MPLS switches. Now that's an interesting thing. So let's go to the MPLS switches. Next one. Look at this slide. So the MPLS switches don't look at the destination address, they don't look at the IP address, they just look at the circuit number and send the packets. So here's the thing, Ethernet header, IP header and payload, we change that to Ethernet header, label, IP header and payload. So this is the MPLS label. Right, 2.5, clear? Why is it 2.5? Now, so everything is already preset. When you set up the blue circuit, these guys say, I want to set up a blue circuit. So this one says, okay, anything that you put, you want to send on blue, please put a number 64, they tell to A. So A will always put number 64 for all blue packets. This guy tells it to R1 that anything you want to send on blue, please send it with a number 3. And this one tells it, please send it number 5. And similarly for the red circuit, those are the numbers. This one will tell B that you should send the packets on circuit number 5, and R3 will say that please send the circuit number 3, and so on and so forth, right? This connection is set up. When the connection is set up, these numbers are negotiated and remembered in the table. Now whenever a packet comes in here, R1 looks at, oh, this is 64, I should send it to 3. Yeah.
If both the blue and red going to R3 are number 3, then how does it know which one is blue?
Yeah, right. The tables are per interface. So it knows that on the interface number 1, if I get 1, 2, 3, 4, 5, that table will tell you which interface to send it to and what number to send it with. And this is another interface. These are two different wires.
So on the other end, it couldn't have been, right?
Huh?
On the other end, from C to R3.
C to R3,
Right,
they have to have a different number because there is only one wire. Yeah.
So the only time that the source needs to know the destination address is during the circuit
Setup. Yeah. Only at the setup, you set up from A to C, you need to know A to C. After that, see, that was one advantage of ATM, was that it was fast switching. You didn't have to do any long match prefix and all that business. You just look up in the table and there you go. Look up in the table, you could do it very fast speed. And the table lookup is not a search, it's an indexing. You go to the third entry in your table, 64th entry into your table and find where to go. Right? So these were some of the advantages of ATM. And the second advantage is quality of service, traffic engineering, and so on and so forth. So that was adopted by IP, and now it is wildly successful. Many things in IP have not been able to be introduced. For example, IPv6 multicasting. There, we have RFCs, tons of RFCs on multicasting, but we don't use it. We have tons of RFCs on mobile IP, but we don't use it. Here, MPLS is used. Okay? So MPLS is widely used. I mean, it's used very much nowadays because of traffic engineering. And you can see that you can do fault tolerance, you can have backup circuit, lots of stuff. All right. Any question about MPLS? That was too slight introduction to MPLS, the fastest that one can get. MPLS is such a big, lots of RFCs, yeah.
Do you think that this will bring over IPv6?
Oh, no, there's not competition. IPv6 and MPLS can live together, except that IPv6 has been around for 16 years but not around. MPLS came in 5-10 years ago and it is around everywhere.
So MPLS is inside the land, right?
MPLS is not inside the land. MPLS is between the cities. So you can set up a circuit from Boston to San Francisco.
No, it's not like internet.
Huh?
It's like internet links, it's the same.
Yeah, this is internet. Yeah, it could be inter-AS as well. So yeah, it is. People have circuits, between their companies. So if you have a company which is 5 locations, Boston, San Francisco, and Texas, someplace, Dallas, they will have MPLS circuits.
Okay. So, and the connection, like when you establish the circuits, when you set up the
Then you call the phone company and say, I want to set up a circuit.
No, but, it's not automatic?
You said manual.
Really?
See, the thing is, they had an automatic system. So there is a whole set you can do automatically. There is a whole set of protocol and commands. However, it costs $1 million. And you don't want somebody to just send a message and say, oh, give me $1 million worth of this circuit. You really have to have some 5 signatures on that one. Right? So the switched version of this, which is automatic dial-up, doesn't work. Yeah.
Could you go back a slide? Here, in the example, the above example, you're saying when you have this thick wire, it is actually like a couple of wires divided by bandwidth, right? Different bandwidth.
Each thick wire is like 10 wires here. It could be, less wires. Yeah. Something like that.
So in this example, the numbers refer to a couple of wires from...
No, this number refers to circuit number. Basically, so this is red is one circuit. So yeah, actually you are right. Basically, what it's saying is that all the packets going on this red circuit, which in this case was wire number 3 before, and now here in this example I had shown all wires are identical, but here the wires don't have to be identical. The red circuit could be twice as thick as the blue circuit. So red circuit could use 2 wires, blue circuit uses only 1 wire, 1 thin wire.
Yeah, but I just want to understand, here we have it's the same routers, right? Same link, same points.
Yeah.
Between. And in the other example you have, in the next slide,
Yeah, so this is one circuit and there might be other circuits on the same wires. This is 1 wire, this is 1 wire.
and it's not the same links, right?
Eh?
These are not the same points,
These are different routers.
different routers. So it could refer to either the labeling refers to routers, or it can refer between different.
Yeah, so as I said before, there are two things different. First of all, when we say virtual circuit number, that circuit number changes every hop. Unlike the address, if you put the address on the packet, it will remain the same destination address. Here, even though all the packets are related and they are all going to the same place, the number here is 1, number here is 3, number here is 5, number here is 2. So the virtual circuit number is per hop number. Everybody understand that? Second thing is that it is per interface number too. So the same 3 could appear on another wire another physical wire that this router has. So they can reuse that number. So the virtual circuit number belongs to a physical wire, physical interface. So you could have another number 3 on the same router, on another interface.
So here it could be like in the lower example, it could be 3 in the blue one and 3 in the red one, the first one.
Yeah, this is better here. You see here 3 and 3.
Yeah, but I'm asking if it could exit from the same router.
Yes, if you exit from the same router, if you exit on the same wire, they have to be different number, otherwise it will be confusing. But if you are exiting on the different wire, yes, they could be 3 and 3. All right, MPLS is clear. That brings us to the end of this module. And let's summarize the 3 key points that we learned about virtual LANs first. Virtual LANs will basically allow you to have different broadcast domains. And you could do L1, L2, L3. Then PPP allows you to do point-to-point, and mainly the thing is framing. You learned about byte stuffing. And third thing is MPLS. MPLS allows level switched paths, LSPs. So to summarize the whole layer 3 now. Whole layer 3, we talked about CRC and Mod 2 division. We didn't talk about polynomial representation. Basically we did the binary numbers, so that's good enough. And then uses IEEE, we talked about Ethernet. Oh, sorry, this is not layer 3, layer 2. I'm sorry. Let's summarize the whole layer 2. Then we talked about 802.3, and we talked about truncated binary backoff. Then we talked about ARP, and what is ARP for? Address resolution to connect MAC address with an IP address, and vice versa. And then we talked about PPP, which is used for point-to-point links, and MPLS, which allows virtual circuits in IP networks. So really makes circuit switching in IP. All right, homework. So review exercises, this you do on your own, and particularly as I am recommending people who are a little bit lower on the ranking, in the class, please make sure that you do all of this, because more you practice, the better you will do. So here's the homework related to MPLS.
Homework due on Monday too?
This is due on Monday.
So you have 2 homeworks in the lab here now?
And the lab is due on Monday, and the homework from last Monday is due on Monday. So now here's the thing: if you want to email it to us or to my graders, that's fine. If you are going out of town, we will have a class on Monday. Okay? Yeah.
Why is there a homework 5 listed on the homework sheet? Oh, we got that.
There is not 5C on the, yeah, so I will put it in.
Oh, okay.
That's okay. That is only current up to correct up to current.
Well, it has 4C and then it jumps to 6A.
Yeah, right. So I will put, the new numbers will be put in. But right now you have to make sure that up to 4C your grades are correct. And today is the last day to fix those, okay? So just let me know.